All right, now we're continuing the idea of simple applied minimization or optimization problems. It's similar to the first problem I did with the rectangle of area 400. Here we're going to build a stock pen with area 1.5 million square feet and two rectangular sections using minimum amount of fencing. So what I mean here is we've got this kind of shape that's one rectangle divided into two pieces. And I did steal this from Stewart from the book, by the way. So here's what I've got. It's really two rectangles put together, or you can think of it as one big rectangle and then with a divider down the middle. And I want to know what are the optimum dimensions for this, okay, to use the minimum amount of fencing. So let's say the horizontal width is x and the total vertical is y. And let's see if we can set up our objective function and our constraint. Well, our objective function is the total amount of fencing used. Now, that's not just the perimeter anymore. If this is x, there's 1, 2, 3 of x's and only 1, 2 of y's. And so that's going to be f of xy, oops, not a 9, shift 9, equals 3x plus 2y. The constraint, to make the problem meaningful, is that the area be 1.5 million. So that's very similar to before. That is that the area, which is given by xy, is known to be 1.5 million or 15000. Okay. Now here I didn't want to have millions or thousands or millions here, so this is actually in thousands of feet is the scale here. And I'm using the same trick that I did before. In a minute we're going to see the solve constraint. And that's, I put that in as a graph to make sure I'm always having the right area. Okay, but again, that's not something you have to do for the problem. It's just a cool thing you can do with Sketchpad. So, but that's the first thing we're going to do. We're going to solve the constraint and say y is 1500000 divided by x. Very similar to the previous problem. It's not supposed to be super different. Okay, and then so f now can be expressed as solely as a function of x. It's going to be 3x plus 2y, which is going to be 3 million over x. And now I take the derivative. F prime of x is 3 minus 3 million over x squared. And we set that equal to 0. The 3's cancel out, and I get x squared equals 1 million, or x equals 1,000. It's not plus or minus because it's a length. Okay, and then y is going to be 1.5 million divided by 1,000. And so that's going to be 1,500. So what we're seeing now is that they're not equal. And in fact, it's supposed to be taller rather than skinnier. So it's about 1,000 feet. Remember, these are supposed to be units of 1,000. 1,000 feet in this direction by 1,500 feet in this direction. So let's see if that makes sense. If we made it square, something like this, then we're kind of wasting because we use extra fencing for the middle. We don't want to make it too wide because the middle is all in terms of x. That is going to tend to want us to make x smaller than y. We don't want to make it all the way like this because that's using a lot of y and not getting a whole lot of area for all the y we're using, all this vertical. And we certainly don't want to make it this. That's really wide and uses 3 long segments. So it's not square anymore for the ideal dimensions. It is 1,000 feet by 1,500 feet. Interesting thing here I have to mention is that there is still a hidden symmetry here, and that's that the 3x, the amount of horizontal fencing we used, is 3,000, and that's equal to 2y. So in fact, the amount of horizontal fencing used is the same as the amount of vertical fencing used. There's a cool hidden symmetry there. And it's a little bit subtle as to why that's working. You probably don't want to try and use that as a way to guess the answer in any kind of complicated problem, but there are actually some beautiful symmetries that come out of this. But regardless of that, using this method of solving the constraint to eliminate a variable, looking at the new objective function as a function of one variable, taking the derivative, set equal to 0, solve, is giving us the answer. Now again, to be careful, we really should do like a first derivative test or a second derivative test. So for example, f double prime of x we'd want to check that that's greater than 0, but that's very similar to the other problem.